Delta difference, small but finite. Physics by example. In this series of videos under delta difference, we would work out a problem in physics, but take it as an excuse to discuss some basic principles of physics related to that particular problem. This is a problem from Irodov 3.307. A pie-shaped conductor is located in a uniform magnetic field perpendicular to the plane of the conductor and varying with time at the rate dB by dt equals 0.10 Tesla per second. A conducting connector starts moving with an acceleration w equals 10 centimeters per second along the parallel bars of the conductor. The length of the connector is equal to L equals 20 centimeters. Find the EMF induced, find the electromotive force induced in the loop t equals 2 seconds after the beginning of the motion. If at the moment t equals 0, the loop area and the magnetic induction are equal to 0. Just remember this, at t equals 0, that is in the beginning, the loop area and the magnetic induction are equal to 0. The inductance of the loop is to be neglected. That is, the self-inductance of the loop has to be neglected. You can see clearly this is a problem related to the electromagnetic induction. As usual, we have to draw the picture for the problem. The first step in solving a physics problem is visualization. You should be able to picture the situation in the mind, or you should be able to draw it on a paper and think what is happening in terms of physics first before we try to connect formulas and principles to that, physics principles to that. Here, a pie-shaped conductor. This is what we mean by the pie-shaped conductor. Okay. On the pie-shaped conductor, we have a rod moving this way with an acceleration of 10 centimeters per second square. The rod was here first because the area was 0, it was told, t equals 0. The area was 0, therefore the area enclosed by the rod and the pie-shaped conductor was 0. So we will say the rod is there at t equals 0, it was here. And then there is a dB by dt. That is, there is a time varying magnetic field. The problem somewhat misleads for some people, like he says it is uniform field, and he says first, and then it is changing at the rate dB by dt. What it means to say is the magnetic field is pointing outwards towards the, us, but it is spatially constant. But the arrows of the magnetic field are changing with time. So that's what you mean by uniform, but time varying magnetic field is there all over the space here. Like not to crowd the place here, we showed that thing this way. This small circle and a dot in the middle is the tip of the arrow. The field is pointing towards us, to the viewer there, and it is changing at the rate 0.10 Tesla per second. So there are two things here. The rod is moving, and as well the field in this region is changing. So as a result of which it appears an EMF is going to be developed between the ends of the rod, and due to which a current might flow. For example, if this end was going to become plus and if this end is going to become minus, or the other way, we'll see it, the current would be flowing like this. But right now in our what you call problem, we need to find out only the EMF, not the current. Probably in this case, I think this becomes plus, that becomes minus. That we'll check later by the rules. All right. Now, how do you solve this question? When we see this question, the first formula or the first formulation which comes to our mind is Faraday's flux rule. The EMF induced is equal to the negative rate of change of flux. Okay, that is E equals minus d phi by dt. But we know flux is equal to B into A. In fact, it is BA cos theta, but in this case, this cos theta is 1, or it could be minus 1, doesn't matter, depending on the directions you are choosing for A and B. So it is BA. So in the place of flux, we would put BA and differentiate it, because both are changing here. Area is changing, magnetic field is changing. Just to differentiate this with the product rule, we'll think first A is constant. Okay, we'll think that area is constant and differentiate B with respect to time. A dB by dt plus B we think to be constant and dA by dt. So the flux rules gives us this thing, that is minus A dB by dt plus B dA by dt. That means it also tells you that flux can change in two ways. One is the field itself can change with the time, and second, area can change with the time. Or more correctly, of course, this area can change the time in many ways, but in this particular case, the area rate of change of area is nothing but the rate of change of area swept by the rod. More correctly, what I was trying to tell you was, supposing this thing was not there also, which one? This end is not connected also. That means if there is no flux linking through this area also, still I can give a meaning to the that is B dA by dt. Let me tell you more clearly outside here. In this case, of course, this pi-shaped conductor is connecting the two sides, but here I will not connect. So it doesn't mean that now there is no EMF induced. In fact, this particular, which we call as motional EMF, we'll talk about this later, when rods move across magnetic field to cut through the lines of force, not move in between the lines, but actually they should be cutting through the lines of force. In all such cases, the EMF induced will be written as B into dA by dt, which actually means the rate at which the area is swept by the rod than the actual area where the flux should be enclosed. So that is what we are trying to tell. So there are two parts in it. One is A dB by dt, the other is B dA by dt. Now, without even knowing why this is happening, by applying this flux rule, why actually in physics, you see, most of the laws are derived from the experiment, the basic laws. So when this such a law is framed by experiment, you won't be knowing the reason why this law is working, but it works. The experiment is there in front of our eyes, so you cannot this experimental results are wrong. So one way of solving problems is, in physics problems at this 11th and 12th level, is you can take the experimental laws for granted and first try them, use them and get your answers. But of course, you don't stop there. You should learn a lot more after that. That's what we'll be doing today. Now, just find out our numerical value of the what you call EMF induced between the ends of the rod. Now look at this. We'll take the here we had two parts, A dB by dt and B dA by dt. We'll take them one by one. First, we'll address this A dB by dt. So at t equals 0, the rod started here. B was 0, area was 0. At some time t, the rod is here, whereby it moved a distance x. Okay, the length of the rod is in general x. It is given as 20 here. So area at any instant is length into breadth. We could write Lx. Therefore, A dB by dt will be Lx. dB by dt is given in the question itself. That is 0.1 Tesla per second. So Lx into 0.1. L is there for us. Isn't it so? That is L equals 20 centimeters. 20 by 100, we convert that into meters. X, of course, is unknown, and dB by dt is already given. So x we need to find out. It was told that rod starts from rest and moves with an acceleration. So x will be equal to half into a into t square, the kinematics equation. So substitute the values and you'll get x again as 0.2. L was 0.2, x is 0.2, and rate of change of magnetic field dB by dt is 0.1. Yes, therefore A dB by dt becomes 0.2, 0.2 into 0.1, 0.004 volts. So the first part is taken care. Now let us look for the second part, B dA by dt. Yes, B into dA by dt. A is Lx. But L is a constant. Length of the rod is a constant, so L is taken out. Dx by dt. So BLV we got. You must have noticed that this is a formula for the motional EMF. When a rod is moving across a magnetic field, we were told that motional EMF induced between the ends of the rod is BLV. That's what is coming here when we do B dA by dt. Just to make a note of it, we'll be talking about it again. Now dB by dt, now of course L we know, 20. Neither V we know nor B at this moment we know. So we'll go for the other thing. dB by dt equals 0.1 and separate the variables. dB equals 0.1 dt and integrate between proper limits. So 0 to B, 0 to 2, 0.1 dt. So B equals 0.1 into integral dt, 2 minus 0, we get 0.1 into 2. It is simple integration. So B equals 0.2 Tesla at this moment. So out of BLV we have L, we have B. Next job is to find out the speed of the rod. That can be calculated from where? V equals 80, U plus 80. Another kinematics equation we are doing here. So we'll get it as 0.2. So all that substitution will give you B dA by dt equals what? 0.2 into 0.2 into 0.2, 0.008. So the total, the second part is over. B dA by dt is over. A dB by dt is already over. So when you add them up, you'll get 0.0012 volts. Minus, of course. The minus sign is there to explain what you call, it's energy conservation basically. It comes from Lenz's law. That is, the EMF induced and the current induced will be opposite to the change that produced them. That is, what is them here? EMF and current. So EMF and current are induced because the rate of change of flux basically. So they will be in such a way that they oppose this change of flux. That's why the minus sign comes. So we do not bother about the minus sign for that reason here. So I dropped it out and we wrote 0.0012 volts as the EMF induced between the ends of the rod.